Look up on a clear night, and you'll notice a distinct difference. The stars flicker and pulse chaotically, while the closer planets hold a steady, piercing shine. Drive down a hot asphalt highway in the summer, and you'll see a shimmering puddle of water blocking your path. But as you get closer, it completely vanishes into dry road. Or look out after a heavy rainstorm, and you might see a massive 7-color arc materialize out of thin air across the sky. We trust our eyes to give us an accurate picture of the world, yet these everyday optical illusions prove that the visual data we rely on is actively bent, broken, and manipulated by invisible forces long before we ever perceive it. To figure out what is actually real, we have to track a single beam of light from its cosmic origin, follow it as it punches through Earth's atmosphere, and watch how it interacts with our biological hardware. Human vision requires the brain to decode an incredibly perilous, millions of miles long physical journey. This animation shows atmospheric refraction in action. When a straight beam of light crosses into a pocket of air with a different temperature and density, it abruptly changes speed and bends its path. Because stars are so far away, they hit our atmosphere as single-point sources of light. As that fragile beam passes through turbulent, shifting air layers, it gets knocked off course repeatedly, causing the rapid flickering we call twinkling. Planets sit much closer to Earth, meaning they appear to us as broader disks. Their light comes in from a slightly larger area, which allows the incoming beams to average each other out and bypass the atmospheric turbulence entirely. This same light-bending physics happens right at ground level, creating the inferior mirage you see on a hot highway. This diagram illustrates the mirage mechanics. Green rays from the palm tree travel through cool air, collide with extreme heat above the ground, and bend upward toward the eye. Because the brain assumes light travels straight, it projects the origin downward, interpreting the reflection as an inferior mirage of the palm tree. Earth's atmosphere operates as a massive, unpredictable lens, constantly altering the trajectory and integrity of incoming data before it ever reaches us. Under the right atmospheric conditions, a beam of light breaks apart completely. White sunlight hits a raindrop. It refracts and undergoes dispersion, splitting into the 7 colors of the visual spectrum. The spectrum bounces off the back wall through internal reflection, exiting the water and refracting a second time to project those colors across the sky. A rainbow is a massive, natural data decoding event. It takes seemingly plain white sunlight and reveals the hidden, colorful building blocks inside. After surviving the atmosphere, that light finally meets its destination, the human eye. It serves as a biological camera, specifically evolved to catch these wandering rays. Light passes through the clear cornea, slips through the pupil, and strikes the lens. Ciliary muscles squeeze and pull the tissue, adjusting our focus. By manipulating its shape, the lens casts a sharp, upside-down image onto the retina at the back wall of the eye. Of course, this biological receiver has physical limits. If the eyeball is misshapen or the lens loses flexibility, the incoming data degrades. The light focuses slightly in front of or behind the retina, resulting in visual defects like nearsightedness and farsightedness. Experiencing a perfectly focused reality requires extreme microscopic biological precision to catch, bend, and process light that has just traveled tens of millions of miles. Once the retina converts that light into electrical signals, the brain takes over the processing. And it relies on a highly specific biological glitch to make sense of the world, a phenomenon known as persistence of vision. When you look at an object, the impression of it lingers on your retina for exactly 1/16 of a second, even after the object itself is completely removed from your sight. Look at this rapid sequence of still frames. If we flash them in front of your eyes faster than that 1/16 of a second delay, your brain bridges the gaps. The individual pictures instantly blend into fluid, continuous motion. We leverage this neurological quirk constantly. This specific biological illusion allows all film, animation, and video screens to function. If we reverse the journey, pulling back from the visual processing centers of the brain, flying out through the pupil, rising above the clouds, and returning to the vacuum of space, we see the full scope of human sight. Our colorful, moving world is a delicate, continuous dance between the harsh physics of the universe and the biological machine